Hello students, welcome in this video. In this video, I will be discussing with extreme values of two variable function. The topic is very important and interesting. Before we start, extreme values of two variable functions, we need to understand the concept of two variable functions, limit of two variable functions and partial derivative related to two variable functions, which I have already uploaded. If you have not watched, then you can check out the playlist and find the videos related to partial derivative. And let's start the topic local extreme values. Okay, local extreme values deals with local maxima and local minimum. So let us start the definition. If a function is there z equal to f of xy and it is defined in a region R where AB belong to R, then number one, z equal to f of xy is said to have local maxima at AB if f of AB is more than or equal to f of xy for all xy in open disk centered at AB. What does it mean? If a point AB is in the region R where the two variable function z equal to f of xy is defined, then f of xy, the function, is said to have the local maxima at that particular point AB if value of f of AB is more than all the values of f of xy within the disk where the center is AB. Alright, so secondly, z equal to f of xy is said to have local maxima at AB if f of AB is more than or equal to f of xy for all xy in open disk centered at AB. Students, you can see a term open disk. Open disk is in fact collection of all the points. Let us write the meaning of open disk. Open disk, so we can write open disk of radius R is in fact collection of all the points less than R units from the fixed point. This is for open disk, and here we get all the points which are at a distance of R units from fixed point at a distance of less than R units from the fixed points. So this is the disk, and here we need to understand if the given two variable function has local maxima at the particular point AB, then it means f of AB must be highest along all the values of f of xy within this disk. Similarly, if the function z equal to f of xy has local minima at the particular point AB, then it means f of AB must be lowest out of all the f of xy which are within this index. This is the meaning of local extrema of the given two variable functions. Have a look. Now one more point is there, critical point. Critical point, what is it? If z equal to f of xy is two variable function, then points where number 1 partial derivative of x, partial derivative of given function with respect to x, partial derivative of given function with respect to y, both are 0. Second, or partial derivative of x not defined, or partial derivative of y is not defined, or third, both are not defined. So it will be more clear from an example. Let us take an example, and now let's find out its critical point. So first of all, we find that partial derivative with respect to x. With respect to x, then y will be constant here. So the derivative with respect to x, y, and here 2x, this will be 0, and this will be minus 2, 0 and 0. Partial derivative with respect to y, and here we get x, this is 0, minus 2y, 0, 0, minus 2. For the critical point, we need to write z sub x equal to 0, which gives us y minus 2x minus 2 equal to 0, equation 1, and again z sub y equal to 0, which gives us x minus 2y minus 2 equal to 0, equation 2. Now solving these two equations, what do we get? Here, solving both the equations, we get 2 minus 2. And this is the critical point of this function. Have a look. Now one more important point is there, saddle point. What is saddle point? If AB is the critical point of z equal to f of xy, then AB is said to be saddle point if there exists some f of xy which are more than AB, and there exists some f of xy which are less than f of AB in open disk centered at AB. Here we need to understand, if the given function z equal to f of xy does not occur maxima or minima at AB, then that is the special case that will come under the saddle point. So in this case, we will get some xy within that disk which will be showing the values which are more than f of AB. Again, there will be certain xy where f of xy will be being less than f of AB. See an example. We have x square minus y square. Now here, for the critical point, we find partial derivative with respect to x, which gives us 2x, partial derivative with respect to y, which gives us 2y. Now here f of x equal to 0 gives us x equal to 0, and f of y equal to 0 also gives us y equal to 0. But the main thing is that here at 0 0 we don't get the given function is showing its maxima or minima. How? Look, here along x-axis what do we get? F of x0, x square, which is positive, along y-axis f of 0y, which will be minus y square less than 0. So in open disk centered at 0 0, there exists some f of xy more than 0, and there exists some f of xy less than 0. So we can say for this function the critical point 0 0 is the saddle point of this function. Have a look. Now one more important point, derivative test of local maxima and minima of two variable function. Okay, for that we need to understand first of all this discriminant. This is called, this expression is known as discriminant of the two variable function z equal to f of xy. Here if the value of discriminant is more than 0, then only we can apply the derivative test. So we need to first of all determine whether the discriminant is more than 0 or not at the particular critical point. So here we need to understand, if z equal to f of xy is a two variable function which is continuous and differentiable in the disks centered at the critical point AB, then at that critical point AB the given function will be getting local maxima if fxx is less than 0. Means the two variable function z equal to f of xy will be getting local maxima at the critical point AB if the discriminant is more than 0 at critical point, and at that critical point fxx is less than 0. Secondly, if fxx is more than 0, then that will be the case related to minima, and this is the important point. First of all we need to check this, the discriminant must be more than 0. If discriminant is less than 0, then the critical point will be a saddle point, and about saddle point we have already discussed that the saddle point will not give the case related to maxima minima. And fourth, if the discriminant fxx fyy minus fxy square is 0, then the test will be inconclusive. Here we cannot conclude anything. Okay, so this is the derivative test, and this is the process to determine whether the given two variable function has local maxima or local minima or not. So have a look. A problem related to local maxima minima. We have a function f of xy, let this be z, or simply we can write f also, xy minus x square minus 2x minus 2y plus 4 is continuous and differentiable for all xy belong to R2. For every real number, the given two variable function is continuous as well as differentiable. Now we have f equal to xy minus x square minus y square minus 2x plus minus 2x minus 2y plus 4. Now with respect to x, if we differentiate, y will be variable. So here we get y, here we get 2x, and again here we get 2, remaining all 0. Y, now y is variable, x is constant, here we get x minus 2y minus 2. Again we need fxy. It means we have to differentiate this with respect to y. When we differentiate this with respect to y, what do we get? Look, y with respect to y will be 1, and now these are constant. We get fxy equal to 1, and fxx, differentiate fx with respect to x, we get minus 2. Fyy is also needed. Fyy with respect to y, when we differentiate, again we get minus 2. For the critical point, we need fx equal to 0, which gives us y minus 2x minus 2 equal to 0, that is 2x minus y plus 2 equal to 0, equation 1. Again f of y equal to 0, which gives us x minus 2y minus 2 equal to 0, equation 2. Solving 1 and 2, we get x and y both are equal to minus 2. Clear? This way, first of all, we need to determine the critical point, and now we have to check the discriminant, and discriminant can easily be remembered by taking the help of the determinant here, fxx, fyy, here fxy, fxy. Now putting the values, fxx minus 2, fxy 1, fxy again 1, fyy minus 2, and the value is equal to 4 minus 1 is equal to 3, which is more than 0. The discriminant is more than 0. It means the given function has local extrema. Now fxx is minus 2. Fxx is minus 2. What does it mean? It means this is less than 0, and the discriminant, let us suppose this as d, and d is more than 0. So the given function f has local maxima at the critical point minus 2, minus 2. Hope you all understood it. Now we can determine the local maxima. Therefore, the local maxima is f of minus 2, minus 2. We can put the values of x and y in this expression, and we get the value of local maxima, which will be equal to 8. So hope you all understood it. In this way, we can deal all the problems related to local maxima and local minima in two variable functions.